Welcome to Spring LIB.
We are given these two half reactions that occur within a galvanic cell. And in part A, we want to determine what the overall cell potential is for this galvanic cell. We know that for galvanic cells, the cell potential has to come out to a positive value. And so in order to do that, we know that we need to reverse one of these reactions so that we cancel out the electrons on either side. So both of these half reactions represent reduction, but one of them will have to undergo oxidation. And in order for the cell potential to be positive, we have to keep the standard reduction potential that has a higher value. And so that will be the one that is reduced since it has a higher potential to be reduced. So the one with the lower standard reduction potential will be the one that is oxidized since it has a lower potential to be reduced and therefore a greater potential to be oxidized. So we see that since 1.50 is greater than negative 2.37, that means we have to flip the second reaction, so we are oxidizing solid magnesium. And when we combine those two half reactions in that way, we see that this is what that results in. And now we have to cancel out the electrons on each side. So in order to do that, we need to multiply the top half reaction by 2 and the bottom one by 3, so that we are canceling out a total of 6 electrons on each side. And now the overall cell reaction becomes 2Au 3 plus aqueous plus 3 Mg solid goes to 3 Mg 2 plus aqueous plus 2 solid gold. And now, since we rearrange these half reactions in this way, we see that the cell potential comes out to a positive value, which is what we want for a galvanic cell. So we add those two potentials together, 1.50 plus 2.37. We see that comes out to 3.87 volts, which is the answer for part A. And now in part B, we need to use the Nernst equation because we are at non-standard conditions. And we know that that means that the cell potential is equal to the standard cell potential minus 0.0591 over N times the log of Q. We can form an expression for Q in terms of species concentrations. The aqueous product is Mg2 plus, so the numerator is a concentration of Mg2 plus, and we cube it due to its stoichiometric coefficient of 3. And the aqueous reactant is Au3 plus, and we square it. So concentration of Au3 plus squared. We are told what the value is of the non-standard cell potential, and that is 4.01 volts. This is equal to the standard cell potential, which we calculated in part A to be 3.87 volts, and then subtract 0.0591 over N. And we saw for the overall reaction, we had to cancel out a total of 6 electrons on each side. So that is why N is equal to 6 times the log of Q, where Q is this expression that we just formed. We have a value for the concentration of Mg2 plus ions in aqueous solution. We are told that that is 1.00 times 10 to the power of negative 5 molar, and we cube it based on that Q expression. Then we divide it by what we are solving for, the concentration of Au3 plus ions, and we square that. And now we rearrange this equation to isolate and solve for Au3 plus. We subtract over these potentials and then divide by this negative ratio, and we raise 10 to the power of whatever that result comes out to be, so that we get rid of this log. And then we can easily rearrange by dividing and taking the square root to solve for the concentration of Au3+ ions. And when we do that, we should get a final answer for the concentration of Au3+ to be about 0.40 molar.